Okay, let's look at one more example of using the ICE method. And this time let's look at a problem that eventually we'll see is going to involve a quadratic equation, which is typically the most involved type of problem you run into, at least in general chem. So let's look at the reaction or the equilibrium between N2O4 and NO2 with that as the equilibrium constant, 1.2. And for this example, we'll start with 0.5 molar N2O4 and let's find the equilibrium concentrations. Once equilibrium is established. And got a note there in the gas phase. So like we did before, we're going to build an ICE table. Initially we have 0.5 molar N2O4, we have no NO2. So to achieve equilibrium, you've got to convert some of your reactant to product, so you're going to lose X amount of N2O4. And since the stoichiometry is 1 to 2, you're going to gain 2X worth of product. So at equilibrium, we should have 0.5 minus X worth of N2O4, and the amount of NO2 is going to be equal to 2X. So our expression for equilibrium is going to equal the concentration of NO2 squared over the concentration of N2O4. Once again, we've got a value for K, and we plug in as much as we know about the equilibrium concentrations. NO2 is equal to 2X, so it'll be 2X, all of that squared. And the amount of reactant is going to be 0.5 minus X. Now previously we talked about how you can simplify the problem by approximating. But remember, approximation only works in cases where you have very small or very large K's. And one clue about whether or not it's going to be okay to approximate is to compare your K with the value you're subtracting or adding X from. 1.2 and 0.5 are pretty close. I mean, they only differ by a factor of really 10. So probably approximation is not going to work here. If it did, this would be a bad example for this video, right? But a lot of times it's okay to go ahead and give the approximation a try, because if it works, then you saved a lot of time. If it doesn't work and you've got to do other stuff to find X, you really haven't lost that much time. So just for kicks, let's just start with the assumption that, what if 0.5 minus X is going to be approximate to 0.5? That would make our equation now equal to this. And as we solve for X, we're going to get X equal to 0.39. Now remember, the rule is that for the approximation to be valid, X can't be any more than 5% of the term you're adding or subtracting it from. And you can just look at these numbers and tell that it's nowhere near 5%. And if you want to, you can go ahead and try to find 5% of 0.5, but 5% of 0.5 is 0.025. So we're way off of 5%. So this approximation will not work. We're going to have to grudge through it the long way. So as you start trying to solve for x, you eventually work your way, or can work your way, to a quadratic equation. Remember, which is ax squared, that's just plus bx plus c equals 0. That's what mathematicians like to call a quadratic equation. So in this case, a is equal to 4, b is equal to 1.2, and c is equal to negative 0.6. If you dig back through your math books, and most Gen Chem books, they'll give you this equation too. You'll see that for a quadratic equation, x is going to be equal to all of this. And part of the term includes a plus minus, so it's minus b plus all of this, or minus b minus all of this, divided by 2a. So as you plug in your values of a, b, and c, you have two possible answers. One is that x can be equal to 0.27, or x is equal to negative 0.57. And for most equilibrium questions like this, one of these can be ruled out. For example, if x is equal to negative 0.57, remember NO2 is going to equal to 2x. So for that value of x, we're going to get a negative concentration. And actually, we're going to get a negative concentration for our reactant as well. Now, you can't have negative concentrations. So you can rule our second possible value for x as being an impossible value for this scenario. Like I said, that's usually the case. One of them can be ruled out because it gives you at least one negative concentration. So it looks like x is equal to 0.27. And go back to when we did the approximation. Notice how far off we were from that answer. So the concentration of N2O4 is equal to 0.5 minus x, which is equal to 0.23. Concentration of O2 is equal, or NO2 is equal to 2x, which gives you 0.54. And remember to always check your answer. You got to take two values that you just come up with, plug them back into the expression for K. If they're right, you should get something close to 1.2. If not, you need to go back and check your work, especially when you have to deal with a quadratic equation.